but they will find the time for you because people are really curious, right?
Lobna, I couldn't agree more. And courage is really important for your audience and for people to realize out there that are listening to this, interview or podcast. Is that a lot of times that's the barrier. Is you have these brilliant people who are very introverted or just not even introverted, but yeah, it's that barrier to kind of blurt out and just say, I need help, or I'd like some of your help. And like you said, and maybe they're worried about someone's time. Maybe they're worried they have a dumb question. Breaking through that barrier, having that courage and building on those wins is so important.
Great. And my question, since we talk, this is a topic about mentor. So, do you have a mentor, or maybe many mentors that you want to share and recognize their effort to help you and support you one day?
Yeah, I've had tons of mentors going to school, just starting in high school real quick, I've had, several professors, from my calculus professor in high school, Mr. Pleta, to people in arts and science and humanities and math who really made me a more complete person, and realizing that it was more than just techie stuff that was, important. Again, having a balance, reading Hemingway, reading books and things like that. They've instilled that in me. But when I got to college, I'd say the biggest mentor I had was really when I got to graduate school. And it was the guy who eventually became my PhD advisor, Dr. Nenad Medvedevich. Studied software architecture, was part of this powerhouse group at UC Irvine in the mid-90s that produced Roy Fielding, who invented the REST architecture, Jim Whitehead, who was the guy that was responsible behind the WebDAV protocol for the web. Basically the protocols of the modern internet, REST, WebDAV, things like that, like Dropbox is built on all of these things. And the people that invented UML, like Argo UML, a tool invented by Jason Robbins. So this group that my advisor came from was this powerhouse group, but he was the most humble guy you'd ever met. He was interested in sports. He had a very small research group at the time, maybe 4 to 5 people, and he was still hungry, not having been tenured yet. I met this guy, and he was only about 10 years older than me. He just inspired me to do research. He showed that someone like me who had diverse interests, and Nino was not on the GPA side. He was brilliant. He was like a valedictorian type of guy. But, that said, he spoke in a humble way, and things like that. And so he was an inspiration to me. Along the line, I've had many mentors, outside of school as well, at JPL in particular, besides mentors around the world. But at JPL, just some people to call out. There was a gentleman named Dan Creighton who believed in me when no one else did at JPL, saw a lot of potential in me as a early developer, giving me a lot of leadership roles. Since then, a couple people, the former CTO of JPL, who's now at Amazon, a guy named Tom Soderstrom, really took, me under his wing and, mentored me to become eventually a CTO at JPL. Really just can't thank them enough. And my current boss, the CIO, Randy Levin, she's just an amazing executive, is really teaching me how to be kind of per your podcast, more of an exponential thinker and leader. I've had a number of people across all backgrounds, genders, ethnicities, and then I've learned a lot from the people that I've mentored as well as part of that. I would say just hundreds to thousands of students across USC and Sri Lanka, getting involved in open source with Apache, just the gamut. I've learned so much from everybody.
Incredible. And as I said before, it's made more about being brave to go and ask the questions and try. Try. Sometimes you found someone who is very open to help you by advices, which is amazing. But you said something that it kept my attention. It's about the humble, and I think from my experience, the most brilliant people are really have this humble way to say things, to give advices, to offer this time, and this knowledge, because they know that you said another thing that I like it as well. It's much more about being hungry all the time, learning, and those people, since they know that they achieve little bit of knowledge, but they are so brilliant, right? They keep being humble, and I like when I meet those people who are really humble, because it's very interesting to say to the young people, whether you are a CEO tomorrow or an executive, and we meet executive, as you know, and we work with them daily. uh, being humble is very important. Keeping feet on, down to earth is very important, because this is the way to be curious all the time. Curious and very open your eyes to the world. Like it's, I like what you said about this. We talk about many topics before going and learning more about your current role. You are at NASA GPL. You lead a team of exponential thinkers. I like saying this because it's the case with data science and software engineering. And I like to mention that there's a lot of software engineering, very brilliant one. It's not about only data science, and we need to say it, right? So
Absolutely.
to build technology that NASA needs to push the frontier of humanity. How was the journey so far, either on the recruiting side or the technical one? And what are the main challenges in such unique role?
Yeah, so I've been at JPL about 20 years, Lobna, and so the first 10 years, I would say at JPL was a lot of learning and eventually realizing how to implement and build these software systems to handle science data. And I got a real good break about 5 years in. I worked on my first NASA mission called the Orbiting Carbon Observatory. This launched in 2009. The first version of this satellite failed to launch, unfortunately, but then they put it up again, and they did a kind of like rebuild the spec. And so the mission actually went in 2014, and there's an OCO2 and an OCO3 and all that. So this mission has a good story at the end. But I learned a lot in implementing and eventually leading the team of people that built that software system. To take the data as it comes down from the satellite, to process it, and to make it available for scientists and decision makers and policymakers. And the big thing for OCO was to look at global sources and sinks of carbon and the absorption of carbon. And the key theory is that the oceans are big reservoirs for it. And the more carbon that's released into the atmosphere, of course, has impacts, in different countries produce more carbon than others. And so it had a lot of economical impacts. And so my experience in working on those projects and there's technically the evolution of systems, we were bitten and smitten by the iPhone age, which was people having these instruments that they could hold in their hands that could take 12 gigabyte pixel images. These are huge pictures. And so the old missions before I started working a decade before them on it, at the end of 10 years, they would take 10 gigabytes of data and they would process tens of jobs per day. When I started in 2005 working on OCO, there was a paradigm shift. In the first 3 months, it was going to take 150 terabytes of data in 3 months, its first 3 months, and then it was going to have to process tens of thousands of jobs per day to handle its data workload. And so that's just, exponential increase on processing and data. And so we had to redesign a new system to do it. I was largely influenced and informed by what was going on in open source. I was getting my PhD at the time. I was involved through that UC Irvine connection with Roy and my advisors, peers
Mm-hmm.
in the Apache Software Foundation. I got involved in the development of Nutch, a web crawler, Hadoop, the evolution of the entire Java ecosystem to do this. And I was applying those lessons to my team and to people at NASA JPL. And the thing I talk about my first 10 years, and we worked on 2 more missions on my team after that. We did the NPOS preparatory project, which is the next generation polar orbiting satellites. And we did SMAP, the Soil Moisture Active Passive mission. And the thing I like to tell people is the big takeaway from that is we convinced NASA and the people at JPL that they could build software using Java, this new language called Java, to do
Yeah.
this, and that Java could realize it. And so that was the culmination of my first 10 years. JPL, I became the chief architect in our instrument and science data systems division. My latter 10 years, and what I'll say, the first 5 of that is I pivoted to technology portfolio management because I had built up this knowledge and teams and people of all of the things that worked and didn't in the missions. And so I had to go get investments and basically from places outside of NASA, because the challenge that we have, I tell people is, NASA is an amazing place, but you build a $2 billion Mars rover or a $250 million Earth Systems mission and instrument. And in that big budget, there's a line item for database, and it's
Mm-hmm.
for like 10K or 50K, in this big project, and so that the reason for that is because they don't, they're still applying IT, kind of an archaic model of thinking about information technology. And they don't fund it like, say, the way that it needs to be funded, like the same other types of, I'll call capital S science,
Yeah.
in that, the physical life, natural sciences. And so you have to, if you want to make if that's your passion, is to do computer science work in NASA, you have to find other technology investment portfolios to kind of get some of that new tech basically in. And so I spent a lot of time working with the defense agency, DARPA, the Defense Advanced Research Project Agency, DHS, different commercial technology, platforms, and getting those investments and building a portfolio so that we could accelerate technology and bring it back to NASA missions. And that's how I got involved in the deep web, and we can talk about that and all that.
Yeah,
But
yeah.
that was my next 5 years. And the last 5 years of my 20 that I've been is that taking all those lessons learned and now basically running a startup, the innovation team in JPL and in the Information Technology Directorate, and applying all those lessons, having to build technology platforms, having done it for real, on missions and science, and then just teaching the next generation who are going to go through that same journey how to do that. I get a lot of the new people at the lab, we bake them up and get them ready, and then the ones that are going to stay are going to all work in space and science and have to go through a similar journey. And so we're preparing them for that.
Wow. We like a couple years ago, you were appointed as the first ever principal data scientist at NASA GPL. Uh, you are known as a visionary and pioneer in such incredible role. We are more than excited to learn about the fascinating NASA and data project that you worked on these last 5 years. You start talking a little bit about some of them right now, but let's go dig deeply on some of them if you want.
Yeah, so I started out, I kind of left the story there in that sort of, year 10 to 15, where I was in technology portfolio development. And one of the things that I learned out of the first 10 years at NASA is that we could improve on search for all of our science data, whether it was earth science or astrophysics or whatever. And so, the fact of the matter was 10 years ago, you didn't go to Google to access NASA data. And you still don't in some ways. And part of the reasons for that is because the data sites and the archives, and I talked about this in a paper in 2013 in Nature called A Vision for Data Science. And basically the archives that stored science data looked a lot, say, like your favorite bulletin board sites that used to exist, like Craigslist or Backpage or things like that. They were behind a lot of clicking to get to the data, a lot of Ajax and JavaScript, so dynamic pages that actually had to be interpreted by your browser. And then when you got to the content, you ordered it in a cart or something, and then you had to wait for it to download. And so that was sort of the experience, and the user experience sucked, and so we wanted to improve that. And so we weren't the only ones that were trying to do that at NASA and science. Around the time, the defense agency, the DARPA, the Defense Advanced Research Projects Agency, was faced with similar challenges, but in a different domain. Their problem was that bad actors were doing bad things, like people were doing human trafficking, they were selling drugs, the early days of this human trafficking phenomenon. They were doing counterfeit electronics, so everyone's concerned about supply chain now. We were working on it about 7 or 8 years ago. And they were doing it, these bad actors, on the public internet, but behind forms, carts, JavaScript, images, videos, things that traditional search engines didn't address very well. And or if they did address it, like Google had the ability to do some of these things at the time, it wasn't generating them revenue or helping generate clicks for their site. And so they had little, incentive to solve these problems. And so DARPA incepted a program called MEMEX. Their goal was to basically make traditional or open source search engines, technologies, or platforms more resilient and more able to do what we call bulk collection of data from the deep web and eventually the dark web. We built the first ever Google of the dark web. And the dark web is basically a different protocol for the internet. There's a browser that you can get called Tor that allows you to browse anonymously sites made available from the Onion protocol, which is a anonymized way of browsing the internet or having internet sites. And so we built the first ever Google because what we found out is that people were doing bad things on the dark web too. So on the deep web and the dark web, people were basically selling, people. They were, doing hitmen. They were, doing illegal weapons and all that. And so we built the technologies that allowed bulk collection of information for that. and that allowed law enforcement or whatever to, adjudicate or to collect information when they needed to solve crimes and help people, in those particular ways. And so in doing that, that also helped NASA because those same technologies, things like Lucene, Elasticsearch, Solar, and things like that, that we improved that provided the capability to, say, crawl like a browser does, process Ajax and JavaScript, handle images and videos, extract out the people, places, and things in them. Those types of capabilities that we added to those technologies automatically made it easier to search NASA data because all of those technologies were deployed in our data centers and archives and things. And so now all of a sudden search engines could reach into NASA data sets, reach behind pages and carts and firewalls and things like that, and basically collect the information that was necessary for scientists to understand what's going on. And so that was a case of law enforcement and the defense agency basically making it so that we could, they're investing really in technology that would allow us to handle that.
This part of dark web versus deep web, if you can explain to us just very quick, what is the difference and what is the main, like, what you discover in this project, or what in more details, if we can, like in few minutes, if possible.
Yeah, so this program, this MEMX program, as an example, had two major areas. It had bulk acquisition from the deep and the dark web, and it had extraction. Once you've acquired content, apply AI, machine learning, and other capabilities to, say, reach into that content, extract people, places, things, locations, and all that from text, from images, videos, and things like that. And so some of the things that it accelerated was the ability to handle multimedia content in frameworks that didn't do that before. So like the application of deep learning and models like Inception for computer vision to take an image and say, what's in this image, object recognition and things like that. And then what are people, or what is happening in this image? So more things like language models and models using natural language to describe what's going on in images and videos and things like that. And so fundamental like improvements in those technologies came out of that. Now, more broadly, what that tech enabled, say, law enforcement to do was to, say, make 419 plus arrests using data that we collected for them, in the human trafficking domain, to have a capability that's now run by several law enforcement institutions in New York, Texas, and other places, and give law enforcement a capability when they get a tip to rapidly investigate that tip to, and in its heyday, we estimated that the size of, say, human trafficking on the web in 2015, 2016 was something on the order of 80 million web pages and 40 million images. And we provided a capability, through that program to collect within a matter of 48 hours the entire scope of those pages and images, so 120 million elements of content, and to be able to recollect it, very quickly on a cloud, on the web, moving from, say, machine learning, theory and Jupyter notebooks and things like that to actually having a pipeline that would collect that type of, thing. In other words, giving law enforcement, and eventually NASA scientists and our data centers the same types of capabilities that big companies like Google had for free, through these technologies, through easy ways of just putting, these open source technologies together, downloading them, and then having your own Google-like search engine or Google-like ability to collect this content and interpret it and things like that. So it helped law enforcement in human trafficking. It helped, places like ATF investigate, weapons and arms trafficking against states or in different states, where they were, dealing in, on these bulletin boards that previously no one was looking at, or that people were looking at, but they had to point and click and get at. It was all very manual. And then all of that tech made its way into NASA data archives in Earth and planetary sciences. So now when you search these things today, you see today that you can actually do some of this stuff on Google. It was directly through advancements from the MEMX program that has happened.
Impressive. And you had me make a transition with the another topic, named trust technology, that is in this series. So let's talk about technology, transparency, and trust. the 3T. As you work on building AI products and services for this humanitarian big mission, how can we build transparent and trust AI technology? It's a crucial question, right? But it's something that everyone is like, at least we are working more nowadays in AI ethics and AI responsible, right? And trustworthy technology. But we are curious about your perspective and your vision about this part.
Yeah, so I'll also help make a transition. So even back in the MEMX days, there were concerns at the time too about bias in our training data, being overly biased to the types of, say, things that we were downloading, either images or scenes or things like that, and not having good representation. So representation is a big deal nowadays. And the pivot from that away from, say, law enforcement and things, in which they're still working on, there's a lot of work to be done, but back to NASA science, is that today there's a lot of work. I do a lot of work in computer vision, but it's for robotics and applying that to, say, Mars missions and things like that. So it's not just, what, say, investigators see, or what we see when we're searching for science data. But now I'm really focused, and our team is focused on, say, helping the next generation of Mars rovers and what they see. Because here's a quick challenge for your audience. The light time from Earth to Mars is about 8 minutes. So it's about 8-minute round trip to send a message to Mars and get a message or receive a reply back. And so because of that, we have several assets on Mars. We had a Mars mission in 2018, InSight. That's a lander that has a big beam in the ground to measure what we call Mars quakes. There was the Mars Curiosity rover, MSL, Mars Science Laboratory, 2012. That's the big car-sized rover, nuclear-powered. There's a big event around that. Obama thanked everybody from the team and all of that, the former U.S. president. So we have several assets both on the surface and around Mars. And so because of that very thin pipe that we have from the Earth to Mars, we have to make use of it very well. So every day, the Mars surface planning team that plans what those rovers on Mars will do for the next day, they get back 200 images a day to decide what to do the next day, because these rovers have cameras on them. And that's not great visibility. They've got to pick, very, meticulously what targets they'll go after and what they can see. But another thing to take into account is that those Mars rovers, because we are risk averse in space, and things like cosmic radiation does all kinds of weird stuff to hardware, and it does things like flips the bits in the hardwares from zeros to ones and ones to zeros. We typically only fly hardware or computers on these rovers that are what we call radiation hardened, or that can withstand that cosmic radiation in those really extreme environments. And so because of that, the types of technology that you and your listeners see on your computers nowadays, desktop technology, aren't available in space. What's available in space and on the rovers today is like an iPhone 1 processor, like what we call